Okay, guess who's back? Back again. Katie's back. Tell a friend. Sounds like a poet. Yes, the famous poet Marshall Mathiovian III. Okay, yes, so like I was thinking in the last stream, I'm going to be working on the Buddhabrot. I don't know what is it. What is it? Buddhabrot. It's not a set. It's probability distribution, whatever that means. So yeah, it's so I think we'll start with just implementing a mandelbrot set and then figure out how to turn that into Buddhabrot. I'm just going to do it the HTML canvas way. And then maybe, I don't think we can do this with GLSL. I don't have enough trust in my abilities with WebGL to figure that out. So yeah, I think this is going to be, yeah, let's just start. I might start procrastinating again. So how do we, let's just do like HTML file. I don't want any build system associated with this. So what is it? Projects. Yes. Buddhabrot. Perfect. Oh, of course, we're going to have Git here because, we are 10x developers. 10x developers always commit their code. There's our source, which will be yeah, script.js. I was thinking, oh, let's do TypeScript or something. Nope, I'm not going to be doing TypeScript. Let's not do two things at the same time. Oh, there is one problem though. I would like some IntelliSense here, but I don't know. I feel like having this would maybe adding TypeScript would give us something because I do have the language server globally installed, but not TypeScript. So maybe that should fix it. Okay, I think it fixed it. I'm not sure. Let's see. Here we have all our shit. We do need a git ignore node underscore modules. All right, let's do that. All right, GCM init commit is the shit that makes me want to do it. All right, here's our browser. Let's open it up this way. Yeah. All right, we've got our code running. Oh wait, script.js not found. I'll have to, yeah. Yep, gone. Okay. We are at an empty file now, finally. Yeah, let's start. Let's do canvas equal document dot create element canvas canvas dot, or sorry, document dot body dot append child canvas. Some boilerplate shit. I should have done this before the stream. I don't know why I always come on here without anything and then complain. 600 I think is fine. Border to just make it visible. White, actually, yeah, white. HTML needs to have a style body and HTML. I don't want the background to just be white because I'll blind myself. What should this be? Just black, just plain old black, and make this white so we see a box. Great, done. We're done. Okay, stream's over. Bye bye. That's it. That's all we're gonna do. No, we need a context. Okay. Oh my god, I just had a stroke for a second. Okay. So first, let's plan this out. So, I mean, first step is just drawing the mandelbrot set. Mandelbrot, I think. Yeah, mandelbrot. To do that, we just need to read all pixels on screen on canvas. Canva. For each pixel, apply zn equals z plus c. Oh, sorry, z square plus c. This is the formula for generating mandelbrot items from the mandelbrot set, and the way it works is I'll just do some more indentation, I guess. Yeah, the way it works is for each one of these items, or for each one of the pixels, we apply this function. We keep applying this function till zn starts tending to infinity. Like it starts growing in value and not stopping. So I think we'll need, I mean, in the stream format, if anyone has any questions, that will help me explain, because I don't know where to start. So basically, for each point, what I'll need to do is I first apply z square plus c, which will give me another point. By the way, z is a complex number, which is just a spicy way of saying 2D coordinates. But yeah, so it takes me there, and then I apply it again for the new point, which takes me somewhere else, and I apply the formula again, which takes me somewhere else. So for every point that's in the Mandelbrot set, the formula being applied will give us another point that's still here, that's not exploding to infinity. Whereas every point that's outside the Mandelbrot set will in very fast just blow up. Like the value will keep going up, so we can detect that, yeah, after a certain number of iterations we can see that this value has gone off the rails. So we for the Mandelbrot set, we ignore those points. We just draw the ones that are in the set. So yeah, here if zn tends to infinity, what do? We plot it. Oh, we don't plot it. We ignore it. Ignore it. Else plot it. Something like that. We'll see. We'll see as we go along. Oh, actually, just 5 seconds. I'll be right back. I am back. Am I back? Yes, I am back. Steam says so. Let me just see how my internet is doing. It wasn't doing too well like 5 minutes ago. Seems like it's doing good. Yeah. Hopefully it stays that way. Let's move on. Yeah, we were drawing this guy. So first off, we need a list of pixels. Let's just get Yeah, I'm not going to bother creating separate functions. Let's just do it all at once. Image data. That's what we want. So cpx.get image data. Okay. So it takes, so x comma y and then height and width. So that will be canvas dot width and canvas dot height. Yay. Step 1 complete. And okay, so we need to do some transformations here, and then we put whatever the transform data is back into the canvas. So to do that, we just do image data. What is it? Put image data. We give it image data x and y. Dirty x, dirty y. What is this? What is this nonsense? I'm gonna have to call HR and report you for talking dirty to me. That's a terrible joke. Let's move on. Let's not focus on that. So for each pixel, so okay, so image data, if you don't know, it gives us a list, a flat list of pixels, which basically means the shape of this guy is, let me just do this. Yeah, so it gives me the R value, the G value, and the B value, and the alpha value, and then it gives me the R, G, B, alpha for the next pixel. So it's a flat list of pixels. So to iterate over it, we'll need to do something like this. So for each of them, we go through this. Oh wait, actually it's data.field. Yeah. Image data.data gives us the list of pixels. And here, instead of just incrementing, we'll have to increment by 4 because there's 4 items corresponding to a single pixel. So that's that. And yeah, here now we have, okay, let's just paint something here. Image data.data I, which is the R value that we're setting here, it will be, let's just make the whole thing red. 1, that's the G value, 2, that's the B value, and this is the alpha value. Let's make the alpha as well 255 because, you know, transparency needs to be maxed, but this, yeah, the image that we get should be just red. Yep, we've got a red square. That's what I like to call progress. Let's turn that into a blue square just to, you know, oh sorry, green square because I incremented the green value. Yeah, we've got a red square now. Now we need to do the formula bit. So the way to do that is, okay, so we need, first we need x and y values for this, right? So in this flat image data that we got, we're just getting index of the pixel component in the list, but that's not helpful because we need the x and y. To do that, we have to convert the thing to x and y. How do we do that? Let's see, row. Row would be shit. Index. Index. Okay, actually, index is not that. Index would be index is I divided by 4. Is that it? So okay, so each component is 4 pixels. Sorry, each pixels is 4 component. So oh yeah, I saw that we have a new follower here, Twitch 191020. Is that a birth date? No. So I mean, if it's a birth date, it's either a 2-year-old or a 102-year-old. So I don't know if that's likely to happen, but yay. Thank you for the follow. I mean, you're probably not here, but still, thank you. Appreciate it. Yes. So we've got the index. I think. I think that's a calculation. Let's see if things blow up. But yeah, row. How do we get the row? So the row is, so the column is mod, correct? Column would be index mod canvas.width. Or wait. Yes, index mod canvas.width. And the height or the row would be index divided by canvas.height. Yes, yes. And also we'll have to do math.floor just in case. I mean, we'll have to do it. It's not just in case. But there we have it. Just 1 second. Let me adjust something here. Yeah. Okay. Back to this. We've got a row and a column, but we don't have our x and our y. X would be, so the x coordinate in this case is, I mean, we'll have to shift it, right? So we are here, if we're here, we need to shift it to the center. So let's like do an offset or something. Offset. X is, offset x would be what? Canvas dot width by 2, and offset y would be canvas dot height by 2, because that's the center, and we just have to subtract that with this guy. So const x is, oh, we also have to scale it, so let's also create a similar thing for scale. Scale offset x is, let's just have it be 1 for now. Yeah, seems to make sense. Does it make sense? Yeah, I think for now let's keep it simple. Yeah, so we've got our x now. X would be a row, no, sorry, column times the scale minus offset, right? Maybe, I don't know. Let's write it down so we can analyze it later. I hope so. Column and then minus the offset. That will bring it. Yes. We've got it. Okay, so we've got our x and our y. Now we need complex numbers. The fun bit. So let's do C. Okay, C. I don't want to bother with typing it again and again. Let's group that into what all do we need? We need to calculate. So first of all, we need a constructor. Let's just do a constructor. X comma y will give us x comma y. And we need squared. Do we need multiplication? No, we don't need multiplication. Let's just do square. So for square, we'll need to create another this. How do you do complex number square? I forgot. Let's sketch it out. A plus id, c plus id. That would be Oh, sorry, a plus ib and a plus ib. It's not multiplication, it's just square. So the value would be a square plus, oh, a plus ib. I spelled that wrong. A square, and then the real part would be, yes, minus b square. B square. Let's increase the font size a bit more. Yeah, a square minus b square would be the real part, and the imaginary part would be ab. No, what is it? Oh shit. ab. Oh, 2ab, right? Because a times b and then a times b. A times b plus a times b, the cross multiplication. Yeah. Okay. I could have just looked that up. I don't know why it bothered. Okay. Square. A square plus, oh sorry, it's not a. Z dot x square plus z dot y square, comma 2 times z dot x times z dot y. Okay. We've got a square, and then we also need addition. So a comma b, we need to add these two together. Yeah, I mean, this is just adding the individual components together. So this won't be, yeah, a dot x plus b dot x, comma a dot y plus b dot y. There we have it. I think that's, do we need anything else? No. Let's see. We'll add something if we need it. Yes, so our fn would be, oh, let's not create a function. Yeah, let's loop over it now. Let steps equal 0. So here we need to see how many steps it takes for us to, I mean, blow up, right? So we have steps less than, let's do 200. 200 for each pixels in 6x 6x. Nah, let's do 20 for now. I don't want to wait for it to reload. Steps plus plus. Oh, this reminds me of the good old C++ days, or C days actually. Yeah, so for each of these we'll need z equals c dot new 0, 0. That'll be our initial complex number. And with this, what we'll need is c dot square the z, and we add c dot add c to it. C is our point, by the way, which we'll create now. This will be c dot new x comma y. I mean, we don't need this to be separate, but yeah, fine. Yeah, this is our formula: z square plus c. Oh shit, what did I do? Yes, z square plus c. So we need to keep doing this till we need some in here. Z dot x is greater than what is boundary? Let's just call it boundary. Once boundary equals let's figure that out later. So if z dot x is more than the boundary and z dot y is also, or z dot y is more than the boundary, we're just creating this arbitrary point outside our origin, where, like a square here, where if the z escapes out of that square, we consider that not a part of the Mandelbrot set. If it is in that square, it is a part of the Mandelbrot set. So if it does escape, we just break out, right? And also we'll have to move steps here because we need to access it right after. Yeah, here. So now we check if steps is greater than, I don't know, 20 iteration. Let's see 10. If it is greater than 10, we change image data. what do we change here? Let's just do opacity, or let's add red. Sorry, let's add green to it. I don't know. This is a bit of a stupid idea. What is red plus green? Is that? Yeah, I forgot. Let's see. Oh, we got a small point here. Let's increase the scale and see. Let's do 10-10. Okay, the point disappeared. Oh no, where did it go? Is it? I'm multiplying it. I don't know. Where did the point go? We have a point here. I don't know if that's even visible on the stream, but there is, trust me, there is a point there, but I want to see what that point is. How do we scale this up? Times 100, right? No, the point disappears when I change the scale. Let's do 2. It disappeared again. Okay, maybe your scale thing is wrong. We need to scale it. So we... Oh wait, do we divide it? I think... let's see. No, that doesn't seem to be working either. Let's just do canvas.width and canvas.height. That'll give us -1 to 1 canvas, right? With the borders. Let's do pi 4. Nothing. Not sure about that. Okay. Let's just make it green. let's make the red component 0 for the ones that are exceeding the limit. Let's move all of this. Let's simplify all of that. Scale it up, bring it here, remove x and y variables, bring it onto a new line. Okay, pretty. It's pretty. Oh, actually, I can just run prettier on the file. Yeah. Oh, I forgot. We need to create a commit. Shit. Follow me for more advice on how to write better commit messages. Where were we? Okay. So it just formatted it into a single line. Alright. Oh, my back hurts. God, I need to get a gaming chair. That'll be fun to sit on. I'm just sitting on my fucking dining chair right now. I have that as my workspace. What is happening right now? I don't understand. Z square plus C, did I? Okay, boundary is 1, let's make it 2. Let's change the scale to 1 again, because we were seeing something when it was 1, so... Yeah, we're seeing something again. It's a tiny fucking point. How do I move it? I feel like when I'm moving the scale, it's kind of, I don't know, offsetting it somehow. Let's do 0.9 on X. Let's see. Okay, so it's offsetting it for some reason, and it's making it smaller. Let's do 1.1 on X. Wait, why is it moving it to the right? That is confusing. So confusing. Yeah, it's moving it to the right. What the hell? I'm trying to scale it up. Oh, maybe I need to subtract the offset first, right? Let's try that. Let's see. Okay. I mean, it's exactly where it was before, so let's do x 1.1. Nothing changed. Let's do 2. Okay, it's scaled up. All right. I think that's it. Let's do 100. Let's see what we got here. Oh, it's a square. It's an ugly square, but it is a square. Okay. Let's change this to this guy. All right. Let's look into what went wrong. Steps greater than steps 0, steps less than 20, steps plus. All right, that sounds good. C is our point. Z equals c square plus c. Boundary 2. Okay, maybe it's the boundary. Let's set it to 1. Well, here, let's set it to 1. Okay. That's worse than what I was expecting, but alright. Let's do 0.5. I mean, it's getting some shape. It's not what I was expecting, but it's some shape. Okay. First of all, my god, I don't want to look at this red square. It's too fucking terrible on the eyes. Let's make it black by default. Let's make this, if the mandelbrot set, we can make it, I don't know, 200. Let's make this 1 or 200 again. Let's see. Okay, this is much more acceptable. Image data. Okay, boundary. Where have we fucked up? Have I forgotten something? Z starts at 0, 0. We've got z square plus c. And if x exceeds a boundary or y exceeds a boundary, we break out of the loop, which will now give us the number of steps it took to break out of the loop, which we can check and which we paint according to. All of that seems fine. I mean, maybe we fucked up in the square thing. Oh yes, we did. It's minus. Oof. Oh my god. Look at that. First try. I mean, not first try. I fucked up with the square formula, but first fucking try. Look at that. We have stepped on the moon. This is our crowning achievement. I've peaked. This is the best I can do in my life. That's all. We can all go home now. Let's increase the number of steps. Yeah, we get a more detailed image. Let's increase the scale a bit to get a bigger image. There it is. Let's offset this by some value. X, let's move it to the right. Some, maybe 50. I don't know, 50. Yeah, 50 looks fine. Or 70 or 80. Yeah, this seems like it's in the center. Okay. All right. We have a mandelbrot set plot thingy. I don't know what to call it. Let's increase the max number of iterations and make it more detailed. Maybe it'll take, yes, there it is, a lot more detailed. Okay, I mean, right now we have the ability to do increase the max number of iterations, but soon we won't, because the Buddhabrot set takes a lot more computation, so it'll take some time to reload the page every time. But yeah, we have done it. Zoom in a bit. No need. Let's increase the canvas size. No need. Let's start with the Buddhabrot set then. Right? We have our mandelbrot set. Let's move this to here. Or let's just keep it there. Okay. I don't think this matters all that much. Yeah. That's fine. Let's come in. I did it. You know how commit messages go. All right. We have a mandelbrot set. Step 1 completed, and it only took 40 minutes. All right, the second thing to do now is the Buddhabrot set. Buddhabrot set. It's not a set. It's what was it? It's a probability distribution. I knew that. Okay. So there is one. The key difference between the two is it's that we deal with points. So in the mandelbrot set, we are only dealing with points that are inside the thing, the mandelbrot set. But for Buddhabrot set, we are primarily dealing with the ones that tend to infinity. So yeah, rendering method. Is there some algorithm for it that will make our lives easier? Oh my god, logistic map. Don't bring all of this stuff up. I don't know what that is. Oh, that looks pretty. Okay. No distraction. Oh, actually, before I do that, I need to turn on the lights. Just a second. And I'm back. Yes. So, we won't be able to do these. Like, our image won't be as detailed as this is, because I mean, obviously we can't do that many iterations on my 8 GB RAM computer on the browser canvas. That's not going to happen. Maybe with WebGL it might, but I don't know how to do it. Actually, let's see. What is it? Okay, I can't open it. Maybe I can. What was it? I keep forgetting. What is it called? Shit. Shit. It's shader toy. Shader toy. Yes. Let's do Buddhabrot. Okay. Yes, look at that. This seems slightly faster. See how long it takes to print that out. Oh, this looks. Oh, that's kind of pretty. Let's see. Oh shit. Error. Oh, okay. Maybe I can't run it here. Look at that. Oh, I'll have to run it again. I resized my browser. Oh. I don't know how did they do this with shaders. Seems. Yep. Oh my god, it's very little code, but I'm sure they're doing some fancy shit. We can't do all of that because I'm not smart enough to do all of that. We're going to stick to the bare minimum, the basic definition, and then maybe we'll see if we can do something for like do it inside shaders or something like that. Oh, it's too grainy. I mean, it's going to be grainy, obviously, but oh, okay. This I'm tripping out looking at this. So let's come back to Earth. Yes. What relation to logistic map? I hope we don't have to understand what that means. Nuances. Let's just focus on this. Mathematically, the Mandelbrot set consists of, let's zoom it in a bit so everyone can read. Okay. Mathematically, the Mandelbrot set consists of a set of points C in the complex plane for which the iteratively defined sequence, yes, this is what we have already done, does not tend to infinity. Yes. The Buddhabrot set can be constructed by first creating a two-dimensional array of boxes, each corresponding to a final pixel in the image. Each box I, j. What the fuck? Okay. I, j for each point in the canvas has size and complex coordinates of delta x, delta y, where delta x equals width upon m, width upon I, and height upon j. Inverse. All right. Oh, actually, yeah, it's doing it in the scale of height. Okay. For each box, a corresponding counter is initial. By the way, so far I've understood nothing. Let's go with that assumption. For each box, a corresponding counter is initialized to 0. For each box, a corresponding counter is initialized to 0. Okay, some variable. Next, random sampling of C points are iterated through the Mandelbrot. What the fuck? Sampling of C points are iterated through the Mandelbrot set for points which do not escape within a chosen maximum number of iterations. Yes. Okay, so the points that are outside the Mandelbrot set, points that do not escape within a chosen maximum number of iterations, now therefore not in the Mandelbrot set. The counter for each box entered during the escape to infinity is incremented by 1. In other words, for each sequence corresponding to C that escapes during the escape, the box Zn lies within is incremented by 1. Oh. Oh no. Did I take on too much? Points which do not escape within. I mean, I understand part of it, but I'm not sure what it means by boxes. Is it the way we are scaling it? Like, I mean, in our calculations, each pixel isn't just like a pixel. We are representing that as a pixel on the canvas, but in real we're scaling it. Is that what that means? Oh, that is okay. Wikipedia. I've given up on Wikipedia, so let's look at something else. Buddhabrot. Yes. How does Buddhabrot work? I think this is the one I visited. Okay, this was yellow. Buddhabrot uses same iteration rules as Mandelbrot. Thank you. Points are sampled on the complex plane repeatedly, transformed using a simple function, yes, z square plus c, and filtered based on whether they escape to infinity or not, which is what we've already achieved here. The major difference, however, is which points are kept. Yes, if a point does not escape, it is thrown away. But if it does escape, the point and all of its transformed versions are stored. If it does escape, the point and all of its transformed versions are stored. Okay, so for points here, say something here. Okay, for points inside the Mandelbrot set, we know that it won't escape. It will just cycle between values within the Mandelbrot set forever. But for points outside it, it will tend to infinity. So what we need to do is store all the points that we encounter while going to infinity. Does that track? I think so. Okay, let's write that down. Store all. Okay, for values not in the Mandelbrot set, which, by the way, this is the condition that we're using to define which ones tend to infinity. So everything that we're breaking out of are the ones that tend to infinity. So yes, for values not in the Mandelbrot set, what do? We store every point we visit. And what do we do with it? The transformed, okay, and all of its transformed versions are stored. The transformed versions of the point correspond to its trajectory through space as it escapes to infinity. Yes. If we do this many times, we end up with a large list of points not in the Mandelbrot set and their trajectories on their way to infinity. Yes. To obtain a Buddhabrot, we simply build an image representing a histogram of these trajectories. We start with a black image, and whenever a trajectory passes through a pixel, we increment it by 1. Okay, that's what it meant by boxes then. It just is a representation of the pixel. So if it is on a pixel, we need to make that pixel brighter every time we encounter that pixel. Okay, if we keep doing this, we'll eventually obtain an image where bright pixels show regions that are visited often by escape trajectories, and dark pixels, oh, that's pretty. Yes, and by, okay, again, reading it again. We eventually obtain an image where bright pixels show regions that are visited often, and dark pixels, yes, that is, yes, histogram. I mean, histogram means frequency thing, right? Okay, histogram. All right. Okay, let's try it. Let's try it. Okay, like I said, when we are here, we know that this guy escapes. So, okay, we need to track another flag here. Let escapes equals false. Oh wait, did I set the right title for the stream? Let me check. Seems right. Yep. Okay, back to what I was doing. Yeah, we've got our escapes flag. So if it reaches here, we know that this point escapes. So let's just set it to true. Right, and then we need to iterate over the whole thing again. Compute all of this again. Oh no. Let's see. Let's figure out if we can optimize this later. But for now, we can do this. Oh, we can, let's keep printing what we have here. This thing, we'll just draw the rest of it over this one, just for fun. I don't know. Okay, let's make this slightly brighter so that we see the pixels being painted correctly. 50, 50, 50. Yeah, that's fine. Let's see. Yeah, that looks fine to me. Oh, let's store a math separations variable as well. 20 for now, because I don't want to I don't want my CPU to burn immediately. Okay, so here what we're doing is we're calculating whether or not a point escapes out to infinity, which basically means it's not a part of the Mandelbrot set. So actually, yeah, let's figure that out later. We don't need to do this anymore because we know that whatever. Okay, we have to check if we only deal with points that are escaping. So if it does escape, we can just what do we do here? So okay, so we need to now convert z to, let's remove this guy. I don't let's read it first. Value store every point. Yeah, okay. Convert z to index, right? Right, we need to modify a particular pixel that we visit while iterating over it. Oh wait, actually instead of doing this, can we just store the z values? Oh, now I get it. Now I get why it said store the values. Yep. Step, or no, z list. We'll find a better name for it later, don't worry. Let's just push z into the z list. And then instead of calculating that all over again, we can just iterate over the z list. So const z in z list, or of z list, I believe. Yes, of z list. So we have a z, we don't need to calculate that all over again. All we need to do now is convert z to an index here. So to revisit what we did before was we converted the index in our image data to a complex number corresponding to x and y coordinates. We scaled it, we offset it, whatever. Now we need to reverse that to get back the index of a particular pixel. Okay, so for that, IDX, I don't want to collide with the older version, but okay, how do we do this? Z, we have x and y here. What we need to do is, actually let's just copy this guy. First of all, we need to reverse what we did with scaling and offsetting, right? We initially offset the pixel. I'm losing my train of thought here. Okay, we just need to reverse whatever we did here. So we have our row and column. Row would be, let's comment this out so JavaScript doesn't cry. Row would be z.x, sorry, z.y multiplied by scale.y plus offset.y. I hope. Let's see. Let's do the same thing for column. X, X, and X. All right. So now we need to convert z convert row comma column to index. Okay. So we have basically from here, we have a row number. Oh, we may not have a row number actually. We need to math.floor it, I think. Math.floor. Okay, so now we finally have a row number and a column number. Oh, just one second. Okay, back again. Yes, so we have our row and column. How do we convert that to... Yeah, so index would be a row. Okay, no. Yes, row times the width plus the column, right? So if I'm here, I want every row to add up. So every width to add up. So row times width. And then we add whatever column it's on. Oh wait, no. Is it row minus 1? Because we are at that row, but we don't need all of it. So I think it will be row minus 1. Oh wait. Oh, I'm getting a little confused here. So when we are... Yeah, okay, no, it's row because row is 0 indexed in this case. So yeah, that's fine. Row times the canvas dot width plus column. I think that's it. Let's see. Let's image data dot data idx. Let's make it red 255 and see what happens. Oh, we got something. It's not what I wanted, but something. All right. Oh no. Okay, and this is actually the index. What we need is the component, the start of the component. So we need to multiply it by 4, right? Yes. So we need to multiply it by 4 because there's 4 for each corresponding index. Okay, it's not beautiful, but it's something. Let's make it slightly less red. Let's remove red from this guy. So actually, let's remove this altogether. We don't need to see the mandelbrot set anymore. Yes. Okay. We've got a grainy picture. I don't know what these lines are. Okay, I mean, this, all of it seems to be skewed a bit. So I think maybe we've calculated something wrong. Maybe. Let's see. Canvas dot width, scale. I feel like we converted it right. We give it a red now. Okay. Let's do it the other way around. Let's give this 200, and for each image that I'm plotting, I make it 50. Yeah, let's make it gray. Yes. Again, still grainy, but we have something. And also these lines, which I don't understand, but we have it. I'm guessing we're doing some calculation weirdly. All right. Let me think. Let me use my 3 brain cells that are running on full speed. Let's actually change the opacity instead. So we do something like index plus 3, that will be the alpha channel. Let's make that 255 for this. Okay, we got something. Oh, I totally forgot. Um, Here we have a histogram. That we are not doing that yet. So what we'll need to do is we need to increment the alpha channel by some value, so it keeps adding up and brighter ones. Okay, okay, I mean it's very faint, but it's something. Let's zoom in a bit. Yeah. um Maybe. Okay, let's increase the increment 50. Yes. I mean, we still get these lines, which I think is proof that we are doing some calculation wrong. And also this line in the center, which I don't understand. But we have something, which is better than nothing, as the saying goes. Ah, fuck. Oh, is that? No, that's not the offset. It's just something else entirely. Let's change the offset to 0, because yeah, it would have affected both x and y in that case. Okay. Alright, let's add the offset back because I want it in the center. What are we doing wrong? Let's go through it again. Oh, my back is killing me. Okay, is the list. For each list, we plot that out. It escapes. I mean, I think all of this is fine. I don't worry. I feel like this would be the place where the issue is, right? I mean, we are getting some cool shit here, which I can appreciate that it's kind of working. I feel like we're on the right path, but there is something missing. Okay. Index calculation has to be the well, there's some fuck up. Let me go into my into my let me consult with my brain cells. Z dot y plus scale dot y times scale dot y plus offset, and that seems right. Okay. Oh, my brain cells no longer have an answer. Is there any more information here? Important sampling. Rendering the Buddhabrot efficiently poses. We don't need to do it efficiently. You know how I am. Spray and pray approach works reasonably well, but have to sample random trajectories. Doesn't matter. Doesn't matter. Oh, all of these look really pretty. I don't think we'll get anywhere near that, but relation to Jacobian. I've heard that name back when I was forced to study mathematics. Oh, that's neat. That's so neat. Back to Wikipedia, I guess. In other words, response to points do not escape, the maximum number of iterations are discarded. After a large number of C values have been iterated, grayscale shades are then chosen based on distribution of values according recorded in the array. The result is a density plot highlighting regions where Zn values spend the most time on their way to infinity. Yeah, I think that part is clear. The part that I'm having problems with is this guy. Oh, actually, we could have points that are not in. Oh, wait. So, what if z dot y and z dot x are not even in this in here, right? If the row is okay, so if the row is greater than canvas width, no, sorry, height, and column is or column is greater than canvas dot width, we don't do anything. We just did I okay, let's do it the other way around. For these guys, we need to change the color, otherwise we just ignore it, because in those cases the index would be incorrect. Okay, some of it was that, but we still haven't fixed our bug. Okay, I was way too confident with that solution, so back to the drawing board. Row times canvas dot width. That checks out, and plus column. I can't even console log here because the number of items that I'll get in the console log would definitely freeze my computer. What do I do? It's let's actually draw this over the image just to see what. That's kind of neat. That is pretty, a little pretty. It is 200, so yeah. Okay. Now I'm getting rid of that now. What is it? Bing 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 bong bing 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 bong bing. Oh, I don't know anymore. Okay, I'm gonna use the operator here because I haven't used it in like decades. IDX. I mean, I'm guessing this is the part that's wrong. So if the canvas row is less than the height and column is less than the width, yeah, that part checks out, I think, I hope. What am I fucking up here? Is it the row column calculation? Let's see. If row is 0 and col is 0, let's make this the brightest. Oh, sorry, 255, I guess. And let's plot the other ones as well. Plus 0, 1, 2. This one would be 0. Let's make it green because we are not using green anywhere. Oh fuck. What the fuck happened? What did you do? What did you screw up? Oh, IDX is not defined. Oh, okay, sorry. I guess we need IDX up here for this. Yeah, let's see 0, 0. It is not here. Maybe it's too small to see. No, it should have been visible. Maybe let's do if it's math dot absolute row is less than 0.1. Yeah, same thing for column. The shittiest way to debug a canvas. 0.1. Nope, still nothing. Let's create a constant so we don't have to keep doing this. Oh, 0.1. Let's try 2 then. I just want to see where it's closer to 0. Closest to 0. Let's do 1. Nothing. Alright. That is not very nice of you, JavaScript or Canvas. Actually, now that I think about it, this is happening way too fast. Let's do this then. Okay, this is brighter, I guess. 100 iterations. But this is still like pretty fast. I was not expecting it to be quick. Okay. It's a lot grainier, but that's fine. Let's see, let's increase the number of steps here. But I mean, I don't think we need that actually. What can we do to get a more clear image? Maybe decrease this guy. Yes, that seems to have done something. 1 second. What is it? What do you? Yes. Okay. Wow. I am confused. Let's keep it 40. I don't know. Slightly brighter. We don't need that many iterations, so let's bring it down for now. Alright. Much crisper image. But we still don't have an answer for why it's not showing up. Let's remove the offset. Nothing happened. Okay. Back to this place. Let's move the whole thing down. Can't find a solution. Okay. Then, come on. It has to be. Okay. We've got. Oh, it's at the start. Ah, that makes sense. My god, I'm an idiot. I thought it would be here somewhere. No. I was trying to do it with columns and rows, but actually we need to do it with the coordinates. Oh fuck. That's not what I want to do. Revert. Oh, right. That makes sense. We need to reduce this value to something more reasonable. Yes, that's more like it. Let's. Yes, actually that's right. So I don't get it. What is happening? How do we debug this? I mean, okay, so Z and X are going to be right, of course, but we actually need to also check the row and column. So let's do that. Oh fuck. Let's do row here. Point 2 will give us something here which we cannot see because it's too tiny. Let's do 100. This will give us a big square. Oh, oh, okay. Um, does that make sense? No. No, it does not. Why is the index over there? Let's do a smaller value and do console log there, right? Let's do 10. That'll still be a lot of points, but we'll find out why the index is going to the left. Let's see if it is that. We console log Z and we console log row comma column. Let's see what we get here. Reloading. Oh my god, too many points. Okay. Oh, we're getting negative row and column. Oh, something fucky has happened here. Z.x, Z.y. Oh, do we need to offset it first? No, that doesn't make sense. Why is it negative? Row and column should always be positive. So some calculation fuckery. Okay, let's revisit our calculation here. So we subtracted the offset, which brought us to the center. We scaled it down later. So if we need to undo that, we need to scale it up by multiplying it, and we need to add the offset. That is exactly what I'm doing here, but it doesn't seem to be working. What am I doing wrong? Z.x. We increase the offset. We are getting that to be negative. What if I just do let's do math.abs. I don't think that's the solution. I just want to see what I get when I do it. Not much has changed, unfortunately, which doesn't bode well for us because that means we have 2 bugs now, not 1. How do we work around this? Okay, let's focus on the row column issue. It does seem like Z comma Y. So Z starts at 0, and in the right direction it increases, and when it goes down it also increases because it's, canvas has coordinates inverse from what the mathematical coordinates are, partition. So yeah, it still makes sense. I don't know why there's a bright line here. I feel like that's a symptom of what we're screwing up. Let's see. So first of all, let's focus on the row column issue. We are getting some points here, which we shouldn't, because yeah, we shouldn't have negative ones. How are we getting negative values? Let's see. Minus 1.9 and minus 1.48. That doesn't make sense. Minus 1. Can I zoom this bit up? No, I can't zoom I can't zoom in the console? That kind of sucks. No, I can't. You're gonna have to squint if you yeah, if you need to read these numbers, you'll have to squint. Let's look around. Console global, nope. Doesn't matter. Let's ignore it. So what is happening here is I can see a lot of negative row column values, which doesn't make sense. So to figure that out, we need, let me also console log this guy, scale and offset, just see what these are. This is much faster than I expected, by the way, which is worrying me. I guess 20 iterations is not that much, so I guess that makes sense, but yeah, 380 offset and 300. That makes sense. So if I multiply 1.5 with 200, yeah, that also, yeah, that checks out actually. 9,9. Okay, something is weird. Let's try this. I feel like that doesn't make sense, but at the same time I need to grasp its straws, figure something out. Okay, nothing happened. That's not a good sign. What the fuck? Oh, maybe all the points here are outside the canvas. Yeah, actually, that kind of makes sense, to be honest. Yes, that wasn't it. Fine. X can't be negative. Sorry, rho can't be negative. Just so we all know, my brain is working overtime to figure this out. There's only 2 employees up there. They're working their hardest. Offset Y. So let's think this through. So we have a point somewhere. We multiply that by the scale value. And then we add whatever the offset is to zero it out. That makes sense. But there are some outliers where this doesn't seem to be working, which I don't understand why. Bing bong, bing bong, bing 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 bong, bing bong. Bing bong, bing bong, bing bong, bing bong, bing 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 bong bong, bing bing bong. That wasn't me. That was the song. The song that was playing. Column is less than canvas.width. Still doesn't track in my head. you know what? Times like these, you need to look at other people's solutions. Buddhabrot in Canvas. Let's see what other people have come up with. On HTML5 Canvas, do people even type HTML? Oh, JavaScript, Buddhabrot. There's something here. Please. Oh, I can just try it out. Okay, let's see. Yes. Oh, this guy is doing it right. I'm doing it completely in the stupidest way possible, but highest density, iteration limit. Oh, he's using web workers. I was planning on doing that as well. I might do it like split this up into 2 streams. Just do the web worker in the next one. That'll be kind of cool. Dun, 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 Main.js. Bring me the code. Create Buddhabrot, draw, canvas, and it gives it the parameters, state, whatever. It's the libs. JS Buddhabrot. Create Buddhabrot. Canvas drawer. Oh, so many abstractions. Buddhabrot drawer, I guess. Wait, what was it called? Math Buddhabrot draw. Generator. Okay, so it does the exact same thing. Yeah, if yes, so it's just pushing it into the result array, and if it has the result, it returns the array, otherwise it returns an empty array. That makes sense. Random number from plane, random number from plane region. Oh, there is some more complex things to do, I guess. And maybe I'm not understanding the problem right. Density plot. Density plot array. This guy is doing it in a very different way, more performant way, but very different way. I need the simplest and the least performant and the most naive implementation ever. Whoa, that's kind of neat. Trippy too. When does it complete? Does it take, will it do it now? Will it take years? Oh, it has different, like it goes through cycles. Oh, nice. Ah, that's pretty. Okay. Buddhabrot renderer. Okay, he's also rotating it. We don't need to do that yet. Fractal type, infinite is finite. Oh, maybe we can try increasing this guy boundary, because what if we do 5? Let's see. I mean, it's the the max iterations is too low for that to actually have an impact. And still the same problem. Let's keep it at 2. Okay. Z.x is greater than boundary. Oh, it should be math.apps, right? Because even negative ones need to be... Yeah. Okay. Slightly different. It's a bit clearer, but still having the same issue. Let's paint this as well, just to see. Okay, mandelbrot wasn't affected. That works fine. What is happening? What is happening? Image data, data IDX. Still feel like those parts are okay. This is the part that I'm having problem with the negative row and column values. Negative row and column values. Actually, if it is negative, so Z and oh wait, that actually maybe okay, a part of my brain figured it out, but then I spoke and then everything went to shit. So let's just start coding. Let's see if, okay, instead of that, if row is less than 0, we don't need to worry about it. That's what I'm thinking. Oh, actually, I did that wrong, but greater than. Yes. So what I'm thinking is, if it is negative, it doesn't make sense because it needs to be plotted within the canvas width and height. So if the row is coming out to be negative, it means that it can't be plotted on the canvas, right? I mean, yes. So I mean, that solved the problem because we don't have any stray points here now. Okay, part 1 resolved. Now we only have problem with this guy. Yeah, how do we do this? 4 times row times canvas width plus... Okay, I feel like this approach, this is as far as this approach can take me. Maybe we need to consult smarter people, I mean smarter repos like this one, and figure out what the hell they are doing. Iterations, okay, yeah, that's fine. It's painting it in a fancy way, doesn't matter. Oh, it's doing, okay, it's an if else. Let's ignore that bit. Yeah, this is x square plus whatever. Mandelbrot fractal equation. Yeah, that's basically what I'm doing. Okay, so it keeps doing this, and if it is finite, till it is finite, it does that. Okay, push p dot push. P is the list of whatever. P, where is P? Okay, P dot map. My god, mutation inside a map. Use symmetry, doesn't matter. Will rect. What the fuck is use symmetry? Okay, I'm gonna ignore that bit. X. Oh my god. My brain. 30. Let's get rid of some of these. Don't care about this, don't care about this. This is the only one that matters. Iterations. Okay, it colors it however. Although this isn't the Buddhabrot set that I'm seeing everywhere else though, which is funny. Also, I don't understand how this works. We only use points in/out of the mandelbrot set. Yeah, so I mean, wait, what? Yeah, it's either in the set or it's not in the set. What does in/out mean? All points? Fractal type. What is fractal type? Is there a fractal type thing here? Oh, anti-Buddhabrot. Let's do Buddhabrot. Can I render it again or something? No, let's zoom out. Okay, save. Oh, what the fuck? And downloaded the image. Okay, so this is Buddhabrot set. So fractal type. Oh, what does that mean? Okay, fractal type is 1. Means it is okay. I will need to consult the HTML now. Where is fractal type? Okay, Buddhabrot is 0. Let's look at this. So if it is finite, if it is finite, we ignore it. Is finite. What is finite? Control F. Is finite. Where is it? Oh. Oh, is that? Oh no. Is it an inbuilt thing? Let's see. Is finite. Oh, it. Does it actually deal with infinity? Is finite x. Okay. So it does like. That. I don't think I want to do that. But. Is finite x. Yep. Continue. That makes sense. What is x? X is the. Okay. For the complex number, it's the x coordinate. And it rewrites it on every iteration. It's z. X and y are z, basically. Oh, it. I equals iteration. Oh, okay. Okay, so what it's doing is it's doing the exact same thing. If it is, it is literally dealing with infinity, as in, for us, we have a boundary to check whether if it escapes that boundary, it needs to be treated as tending to infinity. But that actually deals with infinity. So, okay, max iterations is 1,000. I guess in that case it does make sense. But, okay. All right, let's keep going. with their code and see what they're doing well. RGB, this is all the painting stuff, right? Use symmetry. What is use symmetry? Use symmetry is make symmetric. Let's not make it symmetric. What does that do? I don't want any fanciness. It's painting the same thing. I don't see the point of that. Okay, I'm spending too much time on stupidity. Actually, you know what? I am gonna go. I'll continue this tomorrow. And if we do it, that's great. We move on to implementing some of this in a worker or something like that. Let's see. All right, I'm gonna go. Goodbye. That's it for me. Oh, that's actually pretty good. I was not expecting my connection to hold up today, but it did. Proud of it. All right, that's it for me. Goodbye. Goodbye.